Okay. So a discrete time signal. So what is a discrete time definition of a unit step signal? Now see this particular definition. U of n is equal to 1 for n greater than or equal to 0 and 0 for n less than 0. Okay. So on left hand side, the signal is 0. On the right hand side, the signal is 1. Okay, got this particular thing. I want you to understand and know the difference between n greater than 0 and n greater than or equal to 0 in discrete time. Now, let us contrast it with the definition in the continuous time. What is the definition in continuous time? U of t equal to 1 for t greater than 0, 0 for t less than 0. See the difference here. Here n greater than or equal to 0 is specified and it starts at 0 only, because after 0 there is 1. There is no 0 0.1, 0 0.2, 0 0.3, so and so. For continuous time anyway, it simply says right after t greater than 0. It says t greater than 0. That means from 0.00001 itself, right from 0, say 0 plus some small value after 1, 0, it has straight away become 1. Okay, are you understanding? Okay, so this is the definition. So from here on, usually if at all there is an x, it is input. If at all there is a y, that is output. The moment you see a u, it's a unit step. Okay, it's a standard notation. It's a unit step. Where do we use it, by the way? This particular unit step is usually used to indicate start of an event. Okay, this is used to indicate the start of an event. Okay, something like what do you say, metering, right? You get on an auto and he turns on the meter. Okay, so starting of an event, or you enter the class, you go to the lab, you turn on the AFO, the audio frequency oscillator. Start of events. It's a the time of reckoning. That's what unit steps usually are used. Okay, let us see. Where exactly? Say here for this particular circuit. So somebody give a reply. Are you listening to me? So here you can see there is this particular circuit, and to start, to tell the analysis, right, when the switch closes, okay, is represented by multiplying with u of t. A t equal to 0 doesn't mean that this starts at night 12 o'clock, right, 0 hour or something. It is a time of reckoning. Now, suppose some vehicle is charging you for every 1 hour. If at all you go to 12:30 for him, he will charge you from 12:30 to 1:30. Okay. So for him, the time you went is the time of, that's when the, charging starts. So here you can see the moment of the switch has been closed is indicated by multiplying this entire thing with the u of t. Okay, that means from now on, so this particular instant will be considered as t equal to 0. From then on, the entire thing will be considered. Okay, that is the usual meaning. Where can you use this particular thing? A u of t can be used to represent much more complex signals. Here is a small task. Okay, what is being asked to us? There is a rectangular pulse given in the figure in the next page, and that particular pulse should be represented in terms of u of t. What is the rule? You can shift the u of t, you can scale the u of t, you can add several shifted and scaled u of t's. You can do amplitude scaling also. Okay, that is the rule. So shall we try? Here is the figure. So what has been asked to us? Represent this thing, this x of t. It's a rectangular pulse in terms of u of t, in terms of u of t and u of t only. So how can we do this thing? How does a typical u of t look like? What does the definition, by the way? 1 for t greater than 0, right? And this continues till infinity. 0 for t less than 0, right? Cool. So now here, how shall I do this? Let me give it a try. So first segment what I will do is wait a second. Okay. Yeah. First, let me take this particular signal which goes till infinity. Okay. Then let me subtract this with this particular second signal which goes till infinity. But this signal say this starts at minus 0.5. Okay, this signal say it starts at minus 0.5. And this second signal, let us say it starts at plus 0.5. Okay, okay. And let me have the magnitude as A. Here also, let me have it as magnitude as A. Now, if at all I add this first signal and second signal, not addition. If at all I subtract the first signal, second signal from first signal, what do you think I am going to get? Can anybody guess? If at all I subtract this particular second signal from the first signal, what do I get? Anybody? Give it a try. Somebody give a reply. Mufid, if at all I subtract this second signal from the first signal, am I getting this x of t or not? Am I? If at all I subtract the second signal from the first signal, am I not getting x of t? Charan, what do you think? Inas, what do you think? Madhav,
So
what do
I think we are going to get.
we are right? So,
Yes, sir.
right, because you can see till 0.5 from minus 0.5, it is 0.5 minus 0. It is 0.5 itself. After 0.5, you can see what's going to happen. A minus A minus A minus A. So you are going to get, of course, this particular signal only, right? You are going to get this signal from minus 0.5 to 0.5. Cool. Now this particular signal, now will you try and represent this signal in terms of u of t? How does u of t look like? Let me draw u of t here. This is u of t with amplitude of
U of
A
t
and
only
starting at
starts from
0. Okay. U of t actually starts from 0. Now this signal 1, does it start from 0? No, it starts from minus 0.5. That means it doesn't it look like a shifted version of u of t? Doesn't this thing look like a shifted version of u of t? Hey, can you represent this in terms of u of t? What if I tell you that you can see the amplitude of u of t as, was 1, amplitude of this is A. So if at all I tell you that I can represent this signal as A into u of t plus 0.5. Do you agree with me? T plus
yes, sir.
0.5 shifted to the left side. Okay, shifted to the signal, shifted to the left side. A into u of t plus 0.5. Do you agree? Reply. Inas, do you agree?
Yes, sir. Yes, sir.
Nutan, Vasudev.
Yes, sir.
Okay. So, on the same grounds, can you express the second signal also? Abdul Mufid, on the same ground, can you now represent the second signal also? This signal. The first signal was on the right side, was on the left side. So I represented A into u of t plus 0.5. Why I multiplied by A? Because this signal has actual amplitude was 1. This was A. So I multiplied by A u of t. This was shifted on the left side. So I did t plus 0.5. Similarly, can you tell me an expression for this?
T minus 0.5.
So that will be A
A
into
U
u of
U
t
T
minus
minus 0.5.
0.5. Okay, are we cool? So you can see This particular
Yes, sir.
rectangular pulse has been represented as u of something like a into. Let us go and see the answer now. Are we correct or what? Yes. Here you can see is the answer. U of t plus 0.5 minus a into u of t minus 0.5. Okay. Got this particular thing. This is how
Yes,
typically
sir.
unit step signal can be used to represent these kind of somewhat complex signals. Okay, let me take you one more. Let me give you one more task. Okay, now here is a signal. 1, 2, 3. Okay, 0, 1, 2, 3. Now, can you represent this signal? Let me call it as some g of t. Can you represent this signal in terms of u of t only? Will you give it a
Sir,
try?
U of t starts from 1 only, like it will have the amplitude only 1, no, sir. But here the amplitude changes.
Yes, yes, amplitudes are changing. So I get to represent. See what is allowed and what is not. I can shift my u of t's. I can add my u of t's. I can scale my u of t's. I can time scale also my u of t's. I can amplitude scale my u of t's also. So how do I do this? How do I do this? What we will do is, let me take this signal 1. Then let me take this second signal. Wait, let me draw little smaller versions. It's taking a lot of space. Okay, what we'll do is, first let us take a unit step. Then we will take one more, which is delayed by 1 second. Of course, going to infinity. Then we will take, okay, if at all I add these two, what am I going to get? Somebody tell me. This amplitude is also 1, this amplitude is also 1. If at all I add these two, what am I going to get?
So we are going to get 1 and 2, like the previous one, like the main question. Yeah, sir, like this.
Till here, right? So for this, if at all I add one more, if at all I add one more, you see here, it is going till infinity, okay? These are going till infinity. Now, if at all I have to add, see this 0, this is 1. Now say one more.
From 3.
2. Okay. Now, what do I get? Now, what do I get? Now, what do I get? See a step.
1, 2, 3,
Step.
infinity.
Yes, I get 1, 2. This is 1. From 2 onwards, again I get one more, right? What is the amplitude now? 1, 2,
3.
amplitude is 3. Now
3.
what I need to do? I need to cut this thing from 3 onwards. How shall I do this? So for that, what I will do? I will take one more signal.
Subtraction.
I will take one more signal which is having width of 3. First, it starts from 3 and having an amplitude of 3. Now I will not add, I will subtract. When I do that, I will subtract this. What's going to happen? This entire segment will straight away be chopped up. Okay, convinced. So this particular signal can be represented as, what did I say? U of t. Somebody, the second one, the second signal, somebody? U of t plus, what is the second signal? Will somebody tell me what is the second signal in terms of U of t? What is the signal? U of
T
t?
plus 1.
No. T minus 1. T minus 1. What about this one?
U of t minus 2.
U of
T minus 2.
minus 2.
2.
Finally, minus of 3 into. I needed a height of 3, right? 3 into U of t minus 3. Okay. Now we can see this x of t has now been represented in terms of u of t. What this particular thing? Why we use elementary signals? So using this elementary signal u of t, I have represented this somewhat complicated signal. Okay. Are you cool with this? So did you understand? Of t and where to use it? So where to use it? Time of reckoning, right from it starts. You enter the class, the metering, right? When it starts. So you multiply by u of t, you will have nothing on the left side. Second thing is to represent this kind of complex signal. Now let us give a try for a discrete time. Remember, discrete time is somewhat much more tricky. Okay. Discrete time is somewhat tricky. Let us try, let me try to represent this signal in terms of u of n. Okay. What is this signal? Now see here. Let me draw this signal. Oh God, it's taking a lot of time. Anyway. Okay. All these amplitudes are 1. Okay. I do not have much comfort in minus. Okay, this is 0, -1, -2, -3, -4, -5, -6. Okay, this is -6. 1, 2, 3, 4. Okay. Now, let us do the exercise in discrete time. I want to express this x of n in terms of u of n. How does u of n look like? U of n looks like this. From 0 it starts. Okay, u of n starts from 0. 1, 2, 3, 4. Okay, and it continues till infinity. Now, will you give it a try? Will somebody give it a try? What is the method?
So we have to get the answer of u of
We
have
have
to
to
get this
represent
equation.
x of n in terms of shifted and scaled versions of u of n.
Okay, sir.
How do we do that?
So first we have to addition. Addition we have to do
Mm,
by adding the discrete lines on the left side.
First, anything you get to see, first we have to decide on amplitudes. It's cool, right? Both amplitudes are here also 1, here also it is 1 only. Okay. So, see, this particular signal starts from -6. So that means first I need a signal which is u of n only, which starts from -6. Okay, 1, 2, 3, 4. We start from -6 and say, let it go and continue till infinity. Then what we will do? Then we will subtract this signal with the signal which starts from 5, which starts from +5. Then what's going to happen is, now if at all I take this particular signal, see this particular signal, this has values till everywhere, this has values. Okay, wait a second. Okay, see here, 4. Okay, 1, 2, 3, 4. Okay, so this is 4 and it has values 5, 6, 7, 8. This also continues till infinity. This also continues till infinity. Okay, now I subtract signal 2 from signal 1. What do I get? Mufid,
Answer.
Charan, what do you think? What's going to happen? Here at -6, what value do I get? Second signal.
So we are going to get -6 itself.
-6 or 1?
So you have added, you have subtracted.
Subtracted. I am subtracting. This is time. -6 is time. The amplitudes of all of the signals are 1 only. Okay.
Yes, sir. I'm saying about not the amplitudes.
So at -6
Just
you
the
get a 1.
-6 amplitude 1 only.
At -5 you get a 1. At -4
1,
also you get a
4.
1. Okay.
So
So
until
till
4 you will
where
get 1.
till where do you keep getting
Until
1s?
4. Until 4. 4, 4.
Until 4. From 5 onwards you stop getting. Okay. Are we cool? Did we not represent this particular thing now? Yes, we did, right?
Yes,
Now we
sir.
could represent this particular 1, 2, 3. Of course, the figures are not good. Anyway, bear with me for that. Now, so That means x of n has been represented now. It is addition of this signal, subtraction of this signal from so this signal with this particular signal. Now tell me what is this signal? Tell me what is this signal? Who is that? Mufid, Charan, Shreya, Nutan, Vasudev. Somebody tell me what is this signal? First signal.
Discrete signal.
Yes, what is the signal?
Discrete time. So in the sense, unit step function.
This is unit step. Unit step starts from 0. If this is unit step, it starts from 0. What is this? This signal is u of n plus 6. Okay. Since this signal has been moved towards the left side, this is u of n plus 6. Okay. This is u of n plus 6. Got this thing? Move to the left side. What about this signal then? What is this signal? This is u of n only. Move to the right side by 5 locations.
N
what is
minus
this signal?
4.
U of?
N minus 4.
No. See. Where does it start from?
5.
N minus 5.
So this is u of n minus 5. So u of n plus 6 minus u of n minus 5 gives you a signal which starts from minus 6 but ends at 4. Okay. Ends at 4. So this particular signal is, this I will represent it as u of n plus 6 minus u of n minus 5. Okay. Okay. Now, before we continue, let us do the same exercise for continuous time. I want you to understand the difference between discrete time and continuous time. Now, on the same grounds, will somebody tell me, say I have a box now, which starts from minus 6 goes till 4, amplitude 1 only. Can you represent this thing in terms of discrete time, continuous time, unit signal? If at all I want to do this for continuous time case, what do I need to take? First, I need to take a signal, unit step only, but which is starting at minus 6. But then I need a second signal which starts from 4 onwards only. Got this particular thing? For discrete time, I wanted a signal which starts from 5 because till 4 I wanted the values to be there. From 5 onwards, I wanted the values to cancel. But here, right from 4.00001, I want the values to get subtracted. For this particular case, my representation of a continuous time signal, which exists from minus 6 to plus 4, would be u of, this would be u of, will somebody tell me what is this? Will somebody tell me what is this? Will somebody tell me what is the signal?
U of n plus 6.
U of, now we are in continuous time, remember. Now we are in continuous time.
T plus 6.
U of t,
U of t.
U of t plus 6. This is u of t plus 6. Where the second one
U
would
of t
be u of
T
T
minus
minus 1.
t minus 4. Are you getting the difference between the continuous time and discrete time? Ihab, you are late. Everybody type a hi, by the way, for the attendance thing. Are you getting the difference, by the way, between the continuous time and discrete time? See here, for continuous time, it was u of t plus 6 minus u of t minus 4. Whereas for discrete time, it is u of n plus 6 minus u of n minus 5. Okay. I want you to understand the difference between continuous time and discrete time. Anyway, we represented this nice. Okay. I hope you understand what is the unit step. So that was the third type of elementary signal. Okay. Are we cool? Now let us continue with the next type. Now let us continue with the next type. What is that? Wait. Yeah. Here we are. Now the next classification would be after unit step. It is called as impulse. I will come to impulse after this one more thing called as a ramp. Okay. Okay. Yes. There is something called as the next thing. That's something called as a ramp. Okay. Have you seen ramps by the way? Anyway, where do you in general English? Where do you use the word ramp? Anybody in general English?
Sir,
where do you use
fashion
the word
shows.
ramp?
Fashion shows.
What?
Ramp.
Ramp where?
Stairs,
Ramp.
no, sir.
Huh?
So in fashion shows, they use the ramp, no, sir.
Ramp walk, right? If a ramp walk, that is not a ramp. Actually, maybe. Okay. Actually, ramp is. Have you gone to this government hospital by the vaccination? Oh, did you get the vaccines by the way? I don't know. They stopped it,
Sir,
right,
it's
after
not.
2-3 days. But in hospitals,
sir.
you might have seen. Besides the stairs, there is this particular slope thing, right? So that wheelchairs can go. Okay, that thing is called ramp. Hospitals, for the stretchers to go. It is not the steps. What they have? They have this plain thing, right? Ramp. You remember in near the mechanical department, in our college also, we have this particular thing. That is a ramp. The thing that slowly increases. Okay. That's a ramp usually. Okay. How do you represent it usually? The representation of ramp is very simple. Okay. So it is given as r of n equal to, wait, let me first show you the continuous time case here. See here, the case for the continuous time, a unit ramp function is r of t equal to t for t greater than 0, 0 for t less than 0. Okay. Or r of t equal to t into u of t. So did you get this particular thing? Let us go to the whiteboard once again. So the definition for a ramp is r of t. Okay, that's the definition. That's the representation. Okay, r. Whenever I say u, it's a step. R of t equal to t. For t greater than or equal to 0, 0 for t less than 0. That means what? At t equal to 1, at t equal to 0, what will be the value? R of t equal to t. For t greater than 0. So at t equal to 0, what will be the value? For t equal to 0, what will be the value?
0.
0. For t equal to 1, what will be the value?
1.
For t equal to
1.
1.3, what will be the value?
1.3.
1.3.
1.3. For t equal to 6, what will be the value?
6.
6.
6.
For t equal to -3, what will be the value?
Minus
0.
0. Okay. So it exists on the right side. On the left side, it is 0. Okay. Got this particular thing. R of t equal to t for t greater than 0. 0 for t less than 0. The second thing, it is equivalent to t into u of t. That means the importance is, it is like at 1 o'clock you go, you get the coconut at 1 rupee. At 3 o'clock you go, you get it at 3 rupees. At 4 o'clock you go, you get it at 4 rupees. But if the shop will be closed, shop will be opened only after 0th hour. That means it is equivalent to t into u of t. That means only from here, this is the time of reckoning. This is the time of reckoning. So this is the definition of a ramp. Okay, represented by r. Okay, so our ramp is also represented as t into u of t. Okay, they usually say that differentiation of a ramp is a step. Do you agree? What is differentiation of a t with respect to time? What is differentiation of a t? Say if at all I differentiate a ramp, It is 1, right? So what's going to happen? If at all I differentiate a ramp, what's going to happen is differentiate t 1, right? I will end up getting u of t. Okay. This is the relation. Or I should say integration of a unit step is a ramp. Differentiation of a ramp is step. Integration of a unit step is a ramp. What this particular thing? Okay. What this particular thing? Similarly, for discrete time, the definition is, for discrete time, the definition is, here. Okay. For discrete time case, what is the definition? R of n equal to n for n greater than equal to 0, 0 for n less than 0. See, this is the thing for continuous time. This is the thing for discrete time. Okay. At 0. Here, see, there is a value at 0.75, 1.25, or 3.333 also. Here, in between, missing. I hope you are getting the difference between continuous time and discrete time. Okay. I hope you are getting the difference between the two. So where do we use this particular ramp thing, by the way? Where do we use this ramp, especially for representation? We usually use this term ramp for representation, acceleration, right? Velocity, acceleration. Okay, that's where we use this ramp thing. Okay, that's where we use. Here some expressions have been given. Okay, so what do they say? Parallel capacitors initially. Okay, the charging of the capacitor they are telling. Okay, change with respect to time. That's what is represented. We also use ramp to represent some complex signals. Also, we usually use ramp also to represent some sort of complex signals. Say something like, I want to represent this triangle. Say I want to represent this particular triangle, 0, 2, 4. Okay. And whose amplitude is, say, 2. Now, this triangle can be represented in terms of ramps. Okay. This can be represented in terms of ramps. Not a comfortable one, but anyway, we can try. We can try. So, how do we do this particular thing? This also, even this particular signal, say a delayed one, say this is 2, and at 2, say this is equal to, at 2, wait a second, say at 4, this is equal to, amplitude of this is equal to, say, 2. This I can see can be represented as R of t minus 2. Okay. And here, any idea? Anybody? Here, anybody? Any idea? So see here, this particular signal, I can compose this particular signal as, say, a normal ramp. If at all I subtract this particular ramp with another ramp, which is starting at 2, what do I get? Somebody tell me. I will send you the invite now. Okay. Be there. Okay. We'll send you the invite quickly.